Good, no problem.
Before we start with this, I was actually curious. I mean, I'm guessing Nick is a no, but Robert, are you aware of, or are you going to the AmeriHack event next month in New York?
No.
Are you
I'll be
going,
there.
Greg?
Yeah, I'll be there.
No.
But yeah, I mean, I don't know what it'll be like, but I don't know. It should be
No.
fun. It's like hacking on, you know, all the tooling and everything like that, and Cabal and whatever.
Mhm.
But uh, But yeah, so anyway, I'll be there. Yeah. Okay. I guess I can start talking about stuff. As I said to you guys earlier before we were recording, I cannot get my screen sharing working. I have some of this talk, especially the first portion of it, in this document that I normally do as slides, so there might be some odd formatting as a result, but it works as a document as well. Um, and Um, and then yeah, the latter part is gonna I don't know, we'll see. We'll see how much of a crashing halt it comes to. We can at least talk a little bit about this stuff. And I don't know, maybe look at some code when we get to the later part. So anyway, the talk overall today is meant to be sort of how to get GHC to do more for you. So like how to write compiler plugins to do whatever you want to do with GHC. And my starter here was basically a compiler, a fairly simple compiler plugin that I've written. I've written a few of them. Some are extremely complex, the most complex is the categorifier, which I've given a talk on at this meetup before, which we used at Kitty Hawk to compile Haskell to C to then put onto a plane. And so that was a pretty complicated plugin that just like rewrote all of the code you put through, and was pretty flexible and used did a lot of other crazy stuff. On the other extreme is this no recursion plugin, which is also the repo that this talk is currently committed in. It's a very simple plugin that basically um, it does what it says on the tin. It just basically makes sure that you're not using recursion in your code. Um, and and yeah, so it makes a good exam. I mean, I personally use it on all my projects. It's now just part of my like template. Like I have this plugin pulled in, and it also makes a good example for kind of talking through GHC plugins because it's pretty simple. And so the beginning of this is kind of how to use that plugin and what that plugin does. And so yeah, so you can see here at the beginning, like to use this plugin, you would basically add those two lines to your Cabal project file, where to any of the stanzas, so your library stanza or whatever, just add the no recursion package as a dependency, and then add the f plugin equals no recursion option, um, which looks for a module called no recursion in all of your dependencies, which exists in this no recursion package, and it loads it up as a GHC plugin. So those two lines is all you need. And yeah, if you do that, probably a lot of your code will stop compiling, and it'll give you some errors. So if you scroll down a little bit, you'll see the errors that come out. Not that great at this point anyway, because there's like no location if it doesn't say where. But it does say like with the name of a function, like at the end, at the top level, the following bindings are recursive, gen graph. And so it says that that function, in this case, is self-recursive. Sometimes you get mutual recursion, or pretty often you get mutual recursion, and then it would list all of the mutually recursive definitions on one line. It would just give you a comma separated list of the yeah the mutual recursive stuff. The second error here is a little different. Um, it's about a method whose default implementation, so a type class method where the default implementation has recursion in it. And it's not as pretty. It has like $C and then sconcat, which is the name of the function or the name of the method. And internally to that, there's a recursive binding, like a let binding, a local binding. Um, and so yeah, those are the kind of two things that sort of happen when you use this plugin on your code. But of course, errors are great, but we like it when our code actually compiles. Um, and so if you scroll down a little bit more to this next section, yeah, you can see here how to get your code compiling again. First, you can just kind of start waitlisting things. This first line sets a plugin option to the no recursion plugin. So basically use that same f plugin opt for any plugin that's there. Then it has the name of the plugin and then a colon, and then everything else is sent to your plugin that you've written. Um, and so this one says allow recursion true, which basically just disables the plugin for this one module, right? If you put this at the top of a module. So now any module that was complaining about recursion with the previous stuff, you can add this to it, and those modules will all start compiling again. But now all you've done is like partitioned your code, right? You have like the modules that didn't have any recursion in them and the ones that do somewhere, and you're just saying it's fine, just let recursion happen anywhere there. Um, and it does work with source annotations too, but I don't like them because they don't work with safe Haskell, and I use safe Haskell all the time. But you can do the same thing with this shorter source annotation that says like annotate the module with recursion, saying that recursion is allowed basically. Um, and if you could annotate the module with no recursion, it would again like disable it if you had turned it on, so you can toggle back and forth. But you can do more specific control over it. So the next couple lines here are passing different options to the no recursion plugin. One is ignore decals, so declarations, and then it takes a list of the decals to ignore, right? So so you can put this again at the top of your module, and when it comes across a function or some term named a recursive fn or another recursive fn, it will be like, okay, I won't check them for recursion. They're allowed to be recursive. And other functions will still continue to error. And then separately, there's ignore methods, which will, because methods aren't top level names, they can't quite work the same way, and so they are partitioned this way. In that here we like ignore sconcat and s times. The default implementations of both are recursive. So unless you explicitly define them, when you define an instance of semigroup, it'll complain about those those methods being recursive, even though you've never, there's no mention of them in your code, but the default implementations are recursive. Um, and Oh, and yeah, and this is like again it doesn't work for sconcat actually, but oh yeah, right. So you can do source annotations again for each individual definition. So this like a recursive function recursion would be the same as ignoring that decal, the a recursive function above. But that only works for decals. That won't work for methods. As I was just saying, like because methods aren't top level names, you can't just put an annotation on them. Um, and so anyway, yeah, so now we've, broke our code and then fixed the code, but like, okay, that was a bunch of stuff to do to not actually get anything. But we do have a couple things, right? We now can um, like get compilation failures, get alerted when new recursion is introduced. Especially if we've done the fine-grained, like allow these things to be recursive, when we introduce new recursive definitions, we'll be alerted to those. Um, and uh, and another is just auditability. Like we can see which things, right, are recursive that we might want to deal with, or and look and see as more things get added. And it's like, okay, we have to watch those things to get, they're called out somewhere that we can maybe have like a script that greps for them or things like that, so we can identify those cases more easily. And so that's using the plugin. And we can kind of, this next part is kind of about like how to get rid of the uh, the recursion, and I think we can kind of, I don't know, breeze by some of this. I mean, like recursion schemes are my preferred thing, but there's
Mhm.
also times when recursion's there and doesn't need to be there, like record updates, which is at the top of the screen right now. Um, like you can just have recursive, like you don't even notice really when you're defining these that this is like a recursive definition. It's like x equals y plus 10 and y equals some value. And Haskell in its laziness is very happy to like do this recursive, um, you know, definition for you. Um, but if you have no recursion on, it will complain at you that, hey, there's this recursion between X and Y here in this record. And so you can then call it out, like just pull out the Y definition, and you can say, okay, X equals Y plus 10. And then you use a little bit of field punning to like say, oh, and I want the Y to be the Y that we define there as well. So this extracts the recursion so that it doesn't exist anymore. You don't have this kind of lazy looping. And that, I mean, that record stuff is can be very innocuous. And again, you don't even know you're doing it. But then it really bites you when you accidentally make a, non-terminating one where y then depends on x somehow, and you get a bad definition that way.
Mhm.
And also, this kind of one of the motivations for writing this was actually that other plugin I talked about, Categorifier, which can't deal with arbitrary recursion. It can deal with some kinds of recursion, um, but it would just blow up if it hit anything, or it would just like keep running and not finish anything if it encountered any recursion that it couldn't support. So this plugin is useful for identifying the things that that plugin would then complain about if it hit them. So it reports them much more nicely than just spinning after the fact. And yeah, I like to use recursion schemes. We don't have to talk about those. Those are something I talk about all the time. And why would you want to get rid of recursion? Like things like totality, right? So making sure that like things will actually terminate all the time. If you can eliminate recursion, that eliminates a large case of non-termination. Um, and then, yeah, like it's a compositionality is something that recursion schemes really help with, where you extract the non-recursive part out. And so by kind of enforcing that you're doing it that way, you can get some nice properties in your code.
Mhm.
Um, So yeah, the next section is like why bother with the plugin? Like why not just write your code with recursion schemes and stuff? Well, it's just recursion is insidious. Like showed you with those record constructors. Like you don't even realize you're doing it half the time. You're just
Mhm.
like writing a bunch of fields, and some of them happen to depend on others, and it just goes like that. And just yeah, you write recursive definitions just without even really thinking about it. Once you get used to Haskell, at least. And maybe it's easier for non-Haskellers to do some of the stuff up front because they're used to doing for loops and stuff like that, and maybe they'd be more explicit. But anyway, um, and let's see, what's the caveats part here? Oh, no recursion. Yeah, we can scroll down a bit more. I can't. Yeah, there we go. Yeah, so it doesn't catch anything that's not inline, basically. So if you're using fuldar, which is recursive, it'll just work. But also fuldars are pretty reasonable function to be using. You can change that by increasing inlining, which there's various options to do that, which would then catch it. And yeah, I could probably like do other things to catch stuff like that. And there's also places that no recursion overlooks for some reason. I'm not sure exactly why, but there are other things that I have to um, identify and catch, but it's already quite helpful. And the next thing, which is actually not a caveat so much as a feature, is that because even though it's a plugin, no recursion doesn't actually ever change your code, right? A lot of plugins, they do something in your code, like Liquid Haskell is a plugin, like Categorifier mentioned, various other things. They all will like do some modification to some internal representation of the code, but something like no recursion is more of a linter, right? It's really just looking at the code you've written and telling you like if you've done something you shouldn't have in some place. And so the nice thing is then you can like use no recursion, but not actually have no recursion show up in your dependency graph, not have your downstream consumers have to have a dependency on no recursion, like a transitive dependency on no recursion. And so the way to do that is have something like this cabal flag, um, defaulting the false and making it manual, which means that the cabal solver won't like automatically switch the value to determine if it can find a solution one way that didn't the other way. We don't need that to happen um, because we basically don't want it by turning it on. If it like automatically switched from the default false to true, it would then just add a dependency, which is not going to help the solver at all. So we just tell it it's manual. We would explicitly be true, and then in your stanza, like your library here, you would add a conditional if the flag is set. Add those lines we saw above at the very beginning, which is the no recursion dependency and the GHC option for the plugin. So it just conditionalizes, those two lines for you. And then in your Cabal project file, if you use Cabal and Cabal project files, you can just add this line that basically says turn on the lint flag. And so that way, when you're doing your own development on your project, it will force that flag on. It will compile with no recursion. But when you publish to Hackage, this flag being turned on doesn't exist anywhere in your package that's been published, so it will be set off for all your consumers who are downstream using it. So you don't have to worry about like, not solving with a good version or other issues like that they might have. This conditional Making it conditional is also useful if you support a lot of GHC versions, but say like no recursion doesn't support all of them. You can just say like only use no recursion on this subset of them, and it should catch the same recursion things on all compilers, although it doesn't. GHC 10 and newer actually do a better job of catching recursion with the plugin. I'm not sure what changed internally, but there's a lot of stuff that's missed in older GHCs that's caught in newer GHCs. So, but anyway, but that allows you to like, not have to have it on every build in your matrix or whatever as well. And if you scroll down a little bit more, if you use stack, it's a little bit different. You have to turn on the flag for each package. So if you have multiple packages that do this no recursion trick in your project, you would have to explicitly tell for each of those packages that you want that flag to be enabled, as opposed to the Cabal one that just says like globally turn on this flag. Okay, so that's like the no recursion plugin, which again, very useful and very simple. Um, and I wanted to kind of now transition to like I do a lot of plugins that are kind of like this, like these linters. I have another one called require for all, which basically forces you to put a for all, an explicit for all if you have more than two or more than one, if you have at least two type variables in your uh, function. So that way it forces you to specify the ordering of them, because changing type signatures can just implicitly change the ordering. And so anyone who uses type applications their code will start breaking once you do that. And you don't even notice it when you're like, oh, I didn't make any changes. No worries. It's a minor update or or a revision or whatever. It was actually a breaking change. And so this requires you to put an explicit for all in those cases. Um, and then yeah, then it's very visible when then you can change the type signature and it won't affect the ordering. And then if you do explicitly change the ordering of those type parameters, then that's obvious in the diff when you're reviewing the code and stuff. So anyway, I just make a lot of kind of plugins that are small and do that kind of thing and put them on stuff that's useful to me. And I think plugins kind of have this uh, not a bad rap, but like I don't know this. Well, I think they're not well documented for one, but also people think of them as you're messing with GHC in some way. It must be like extremely complicated, and there are complicated parts, and we'll talk about like what those are. But yeah, but by and large, like getting started writing a plugin is pretty simple. Um, So here's one of the things that's complicated. When you define a plugin, there are these 12 different fields in a plugin that you can specify or not specify. And it's showing here, the check marks are for my different plugins, which ones they actually use. Um, and and so let's see here. Oh, wait, that's not right. Oh, yeah, that is right. Never mind. I was thinking of require for all. Okay. And so yeah, so there's these 12 different things, and the problem is they all have different internal representations in the compiler and stuff like that, and knowing like which stage is the right stage for you to make changes can be hard to determine. In fact, this red X here on the fourth line, when I first wrote the require for all plugin, um, I defined it as a parsed result action, thinking that was the right place to get the stuff I needed for the plugin. And turns out I was wrong. And it was actually should have been a renamed result action. And so that was, it was like, it's easy to, again, to pick the wrong one. But in this case, actually, these two actions, I think also the type check result action, those three actions, all share a common um, intermediate representation, like all common representation of the code at that point. The difference is there's a type parameter that's specialized differently for each one. And when I first started writing the plugin, I thought like I like to do things fairly abstractly, so I did it generically over, you know, um, that type parameter. Like I didn't specialize it to the parse result action, and so I implemented all this stuff. And a couple of times through as I was doing it, I was like, oh, should I just specialize this to the the particular type that's used here and whatever. And then when I got to the end and I realized it wasn't doing what I wanted, and I actually had to move it to this other one, it turned out, 99% of the stuff I had written um, worked just fine because I had parameterized over that and not specialized it. And so all the code already like worked. I just kind of had to change a few lines that set up the plugin initially, and all the rest of the code was the same code that I had written already. So that was great. Um, but anyway, yeah, there's just a lot of complexity here. Um, the one that well, and so I think if you scroll down a bit, you see there's some descriptions of some of these, and maybe it's not worth it to look at the descriptions. I can talk about um, yeah, okay, you can just scroll up and I'll just kind of describe the relevant ones here. So the first one is not really a hook. It's more about how your plugin affects GHC recompilation. So you can like set this field to another number of values. Like one is just saying that you have a pure plugin, so it shouldn't affect recompilation at all. If no one's changed the code, you don't need to bother recompiling it. Like it's fine. The other extreme is you have an impure plugin, which means no matter what, every time you do a build, you should recompile this module. Doesn't matter if it hasn't changed, because it uses this plugin that's labeled impure. It's always going to recompile it, um, just to make sure that it's got like the right stuff. And then there's a wide space in the middle based on these fingerprints that are basically like a hash of various things that you do care about. And so you can, depending on the options you give to your plugin and things like that, you can say like, oh, the options changed from the fingerprint that was used last time it was compiled, so I should recompile it because it's no longer like we have this indicator that it's not compatible. But it won't just compile it all the time. If you give it the exact same options, and you don't do anything else track anything else in the fingerprint, then it won't bother recompiling it. So that is very helpful in order to like not end up recompiling all of your code all the time. Yeah, if you don't need to. So that's just that kind of control of that. And then all these other things are various hooks. I'm not going to go into all of them, but just kind of especially the ones I've used here. The driver plugin is basically a way for you to like just add compiler flags and do a few other changes to the environment. But basically, it allows you to like say enable a particular language extension. Um, like I forget which one exactly, but require for all has a driver plugin because it needed to it forces on explicit for all, and I think there's another language extension that it turns on. And then I think it sets some warnings up, um, or yeah, it sets up it errors if you omit type signatures at the top level. Make sure that is an error too. So you can't kind of like skip out of having explicit for all by not having a type signature at all. So it basically sets up things like that so that your environment forces you to at least put type signatures in. And then the later part, this rename result action, it's sort of like a pretty source level view of the code. Like it hasn't been processed much yet. And uh, and so this way we know when we're looking at this part that we're going to have a type signature for everything we care about. Because also in this representation, type signatures and definitions are stored separately. It's not like there's some object that says like, oh, here's the definition with a optional type signature. You don't see them together. So you'd have to do a lot of coordination um, if you were trying to manually see if there was a type signature everywhere. So by using that driver plugin and just saying, hey, make it an error if someone leaves out a type signature, I no longer have to coordinate to see if I have type signatures for every definition. That's like taken care of by the compiler already then. Um, and so yeah, so then this rename result action just checks the syntax and makes sure that if there's free type variables in a type, that there is a for all attached to it. Um, and uh, and then this last one that's checked here is this install core to-dos. This is like a deeper level. It's the core representation of GHC, which is very like a type lambda calculus. Um, and it's kind of where you can do real code manipulation. Like you're not dealing with syntax and the language at a syntactic level anymore, but really like the meanings of things. It's a pretty small AST. I want to say like 12 different constructors, maybe less. Um, um, Simon Peyton Jones has a talk, something like I forget what its title is, but it was something like Haskell and eight constructors or something like that. But that was an older version. Like there's been a few more constructors since, but it's still a pretty small AST. And this is like where in that categorifier plugin, we rewrite all the code. Like so at this point is where we can actually see what's happening and what semantically is happening. And so like we can do massive rewrites of things. And this is also where no recursion can see that like there are some recursive bindings because those have all been identified at this point, pulled out no particular constructor. Um, and so it's very easy to identify them at this point, but it's hard to identify them syntax, right? Like, I mean, the whole point of having this plugin is that it's hard to identify recursion syntactically, right? You can't just like look at it and be like, oh, this function is recursive. Um, and so this waits until it compiles down to a deeper representation where that stuff has been identified and then can easily say like, oh, this function is recursive. Um, so yeah, anyway, there's a bunch of these things and there is some complication in terms of knowing which one and when and everything. Um,
How
but yeah,
fast is the lookup to determine like out of a code base, like all the things that are recursive? Is it like you have to traverse like something, or can you
so
say like give me the things that are recursive, and then if
um,
that's empty, then you don't have any or
yeah, so the way that this works, um, it doesn't have to do any kind of like, like database or analysis of the code base because this basically works like compilation unit, so module by module. So as you're compiling the module, it'll just, as each of those definitions gets compiled, anyway, it just traverses the tree for each definition and sees if it has a particular pattern in it. We can actually,
oh I see I think I understand what you mean.
yeah, but let's, Robert, can you go in this same repository, like open a new tab or something. Yeah, just at the top of the repository. And then in the core directory, um,
You guys see the other tab, right?
what's that?
You do see the other tab, right?
Yeah, yeah, we see the
Yeah,
new
yeah.
tab. Yeah.
Good.
Yep. So in the core directory, then there's a
Mhm.
source, there's like core source, and then will be the no recursion. Yeah, that module there. So yeah, if you scroll down, just basically to the bottom of this thing, um, this is kind of like what you kind of have to do at each of these representations that are a little different. Again, this is the core representation, but you have a few functions that kind of look like this collect recursive calls, where you just have a bunch of these different, constructors. So this is the set of core constructors. So how many is it? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, only 10. And so there's only 10 constructors in all of GHC when it's compiled at this point,
Mm.
which is nice. It's not very complicated.
It's kind of fun because it's actually recursive, right?
Yeah, exactly. Um, and I've tried to extract the recursion from this stuff, but because it's a bunch of different types that are all like nested, it's hard to deconstruct that. But yeah, so this is actually recursive. It is for now. Um, but uh, but yeah, so here's like the 10 top level constructors that exist. For the most part, this just recursively calls itself on each of the things, right? So there's an app constructor that takes a function and then an argument to apply it to. And so it just recursively calls, okay, collect recursive calls from both the function and the term you're applying it to. And then there's a case, which is like multiple case statement, like a pattern match. And so it looks at the scrutiny, which is, the case X of, and then all the matches. So it's the X there. And then it does the same thing over the alternatives, but it calls a different function there because alts have another structure, which is like the pattern and then the sub-expression that it matches on. But you can see here that it calls a few different functions like recursive calls for bind, but for the most part, all those do is call back into this on the right subparts, and in some cases just bottom out an empty list. And what this is doing is collecting this recursion record, which is like an instance of recursion happening. And so we're just accumulating those over a particular function definition is what's happening here. And you can see above recursive calls for bind is where we actually create a new recursion record. So a bind, like a let, by the time it gets to this part of whether it's a let or a where or whatever, by the time it gets to this part of GHC, this core representation, it's always called a let. And then the binding can be one of two types, non-rec or rec, so non-recursive or recursive. If it's non-recursive, we're fine. I forget what collect call. I think collect calls is if there's something recursive deeper in, it will append on like the chain of calls of like, so they give you like the scope of some local definition of where it's defined in. And then the recursive case is where we found a recursive binding somewhere, which is again nice. GHC's just pulled that out for us. It's like, hey, here's some recursive thing. And then this basically builds a recursion record that says here's like first it does non-empty on binds, which bind should never be empty, but it's not a non-empty list. So I think I have this changed locally. I haven't published yet, but where the nothing case like errors out or prints a warning or something that like something weird has happened because there shouldn't be a recursive binding with no no variables, no names that are recursive. So anyway, there's a little bit of like.
Are you go? So sorry.
Yep.
Trying to get an idea here. Is this going to error out on the very first recursion it finds, or will it?
No, it's going to collect all of them.
Okay.
Yeah.
Okay, cool.
So all of this stuff, all this recursive function here, this collect recursive calls and recursive calls for bind, it's just accumulating, right? So we're just collecting all these things, and there's nothing about errors or anything yet. If you scroll up a bit, I'm not sure we'll see where the function is. Maybe down. Let's see. Hold on. Down a little bit. This allow. Where is the? Oh, maybe it is higher. Actually go to the top underneath all the imports. There's a lot of imports in this one, but I guess there's not that many. Down a little bit farther, there should be. Oh no, sorry, it is install. Okay, so the function is called install. So search for install in here. I should have known that. That's what I always call it. So this install defines multiple. You could define multiple passes in a single plugin. This only does one pass. It doesn't have to do anything too complicated. But so it defines this pass. It's called this string gets printed out when it's actually installing it in the compiler. That's why it's called add no recursion rule, not just no recursion. But then it's okay. No recursion pass is actually the logic of what it does. And so the guts here, this mod guts is like all the contents of a module, right? It'll have like all the definitions, all the imports, all the things like that you can get out of there. So what we do here is like we have the guts, we get the annotations, and that's the source annotations that I was showing you before, where you could like disable or you could enable allow recursion on certain definitions or whatever. That's what we're collecting here, these annotations. And then where else do we pull out of the guts here? There's MG binds. MG is just mod guts, and it's just for disambiguating any kind of name conflicts. But it's all the bindings, so we pull that out of the guts, and then we pass that to fail on recursion. So scroll down more, scroll down to fail on recursion, and that's where we'll actually like. There it is. Yeah. Okay. So this is where we call our recursive calls for bind, because so each definition is a binding, right? So like each top level function is a binding. So we're starting at that with a list of bindings, basically, with that MG binds that we got out. We have a list of bindings. So now we just call recursive calls for binds, which again does those few functions at the bottom that collects the set of recursive, places that we identified recursion, bubbles them up, and then here's where we decide, like this logic here. We filter this list to determine if we should be ignoring them for any reason. Like you can see, there's ignored decals mentioned there and ignored methods, and so this is just a filter that takes that list, discards any that that we're not going to error on. And then it calls non-empty, which just makes sure that there's at least one element in the list. Otherwise, it returns nothing. And so, so if the list exists, then we will actually, I guess, yeah, here, right, we return left. Either we fail on that non-empty in the case where we found some recursion records. And that will actually be, so this function is nice and like very Haskell-y in that it returns in either, but we actually end up having to throw or use monad fail or whatever it is to actually get the plugin to fail. Plugins don't actually have like a structural failure, like notion of failure. Like there's nothing in them that says like, oh, I'm failing this plugin. You just have to throw an exception, and which is fine. But yeah, but I try to isolate that as much as possible, right? That's why this function is written like just like you would write a normal Haskell function returning left, even though I have to throw it later. But yeah, I mean, I know I went through this a little bit quickly, the structure, but if you scroll back down to the bottom again, again, the thing is like there's these like these recursive calls for bind, collect recursive calls, and then below that, which I'm just covered on my, there we go. The recursive calls for alt. Those are like the three inter-recursive functions that we have to write in order to collect. And again, most of it is dummy stuff, right? Like recursive calls for alt is just calling collect recursive calls again. Recursive calls for bind calls into collect recursive calls, and or actually no, it just yeah, it does, right? For the value of the binding, it'll call collect recursive calls, and collect recursive calls will call itself or call. So these three just call each other back and forth, and that's most of what happens, except for that one case, the plugins.rec case on line 249. And that's where we just say, hey, okay, I've found something recursive. So really, I mean, you get a lot of information out of the compiler pretty simply. I mean, you do have to get some familiarity with like, okay, I have these cases. What do they all mean? Like, what is the thing? But it turns out that like, especially in this case, but in other cases too, like once you find the one thing you care about, there's usually like some level of the compiler that has kind of centralized or identified that for you. I found like the explicit for all. It's just a matter of like figuring out where where the types have been massaged to the right level, and you can kind of identify that information. But you end up with like this kind of one case that does something interesting, and then a bunch of cases that are just being recursive and like accumulating the results that you do in that one interesting case all over the tree. And so writing a plugin is a lot of that, and there is this boilerplate of these recursive functions and stuff, but with all these cases. But it is mostly this boilerplate, and then figuring out which the right level you want to connect into is. So let's go back to the talk at this point, maybe.
I had a question about install.
About what?
Let me search for it again. It's syntax question.
Oh, okay.
No. Wasn't this one? Gosh, no, sorry, install. Yeah, what? I'm not familiar with this. With that, so it's a smiley face at the end. Oh,
right.
what?
I mean, it's just the operator splice. It's just the cons operator. Right. So
it's the cons operator, and the whole thing is in parentheses. Oh, got it. Yes.
Because you see it takes.
Sure.
So this is an interesting thing, actually. When you install a new plugin, you actually get a list of all the plugins that have already been installed. I think the reason for that is to like determine if you want to like insert yourself in a particular position in the order of different passes that happen, if you have to happen earlier or later or whatever.
I get it. But
yeah.
So I think what kicked me, what is this guy? Run 143. It's like a vertical bar. You see this? Is it just
Wait.
my browser?
I think it must be the browser. Yeah, that's just like a cursor from your. If you click somewhere else, does it move it?
Yeah, it was my cursor. Yes, okay.
Oh, yeah.
So if you removed parentheses, you
can't partially apply an operator without parenthesizing it. So
Oh,
I would
okay,
have to like,
right.
I would take like the like,
Right.
I would add an argument to the function called like old passes or something like that, and then I would say like
I
this
get it. Yes,
colon
yes.
new
It
old
was
passes.
it
Yeah,
was not an infix operator. You could have just used it,
right.
but it's an infix, so you have to parenthesize it.
Yeah,
You could. Can you parenthesize this on its own? Can you do? Can you put?
yeah. The cons operator just in parentheses, and
Yeah,
then you can use it as a function. Then you can just put it in function position, like
exactly. Right.
prefix.
That
Yeah.
would be something that I would see more often. That's why
Oh, I
kind
see.
of.
Yeah.
It's sort of like, what is this matrix?
Yeah. I get it. I get it. But you
Which is
see this a lot
not
with the comma operator, right? Like
got
the
it.
comma operator comes up all the time where you're like, oh, and I've got some tuple, and then it's just like the last thing is not set
Yeah,
or
so I
whatever, and
wasn't
so it's like,
familiar. I wasn't familiar
yeah,
with this trick that you can actually
yeah. Oh, I use that
hide the
trick a
fact that
lot.
this is
Yeah,
an infix
yeah.
by
But yeah, you're
by
right. You could also do it in function position, and it would do the same thing if you parenthesize it and then just put
right.
the rest of the argument
Got it,
after.
got it. Otherwise,
But then I'd still have to parenthesize or put a dollar sign in for the rest of that
yeah.
argument. So it's
Cool.
like, yeah.
Okay, I understand. Great. Yeah, good.
But yeah, but just being in this part of the code actually, this is there's a I want to mention the interesting thing here is that like so you're handed when you install you're installing a plugin, you as the plugin are handed all of the other plugins that have been installed, and so like you can do whatever you want with them, right? Like you can like delete them all, just I don't get rid of all the other plugins, only use mine. You can like reorder them, do like I don't think they're particularly easy to analyze. I mean, it's all like functions, I mean, have this like label that's like, oh, add no recursion rule, but otherwise it's just functions. And so there's not like you can do a lot of analysis of them. But I do have, which I didn't think to mention in this talk, but I have uh, a sort of GHC plugin like Chaos Monkey thing, like I think it was Netflix who coined that term or whatever. The Chaos Monkey is like a service that like randomly like shuts down some of their services and like it like helps them find like distributed systems issues by just randomly shutting things down. And so I do actually have a plugin um, that is meant to run like late in the process, like the last thing you install, that is effectively like a thing to like trigger failures in your process by like reordering your plugins and stuff like that. And so and like inserting other plugins that do weird things. And so anyway, the idea is sort of like a chaos monkey for GHC plugins. And that I created that for Categorifier because that was actually like more complicated stuff. And we also wanted it to play nicely with some other plugins. And it was not always easy to do so. But this kind of gives this hook into like, okay, do whatever you want to all the plugins that are there. And so that is a tool that I should bring up, but I had forgotten about for this talk. Okay, so I think we can go back to the talk, the document now. Yeah, let's scroll down a bit. We can scroll past this section because this is what I was kind of describing before about what we did for everything. Oh, okay, so I do. These are not shared. These are not published anywhere. But I had kind of worked up some examples. This is where I was thinking it would start to fall apart if like talking through all this stuff. And I mean also some earlier parts where I meant to go through some more code, but the default plugin like is basically like the minimum code you need to like write a plugin, which is pretty small. Let's go back to the code and let's just talk about like what in that tab. Yeah. So like and scroll near under the imports, but I guess we're already there. Let's see. Okay, actually yes. Sorry, go up to where the plugin's defined. Okay, so to make a GHC plugin, you just define a regular module. It has to have a term that's exported named plugin, right? So just like here on line 43, it's named plugin, and it has the type plug like above plugin, but that's qualified. And then the definition of that is so a plugin is this record that has all those different fields I was talking about, like plugin recompile, like as to whether it's going to force recompilation of the module, the different source plugin parts, the core plugin, some type checker plugins, other pieces like that I didn't talk about. But that's what the plugin is just a record of these various phases that you can attach plugins to, and you can define whichever ones you want. So normally use like this is a wrapper I have called default pure plugin, which I'll talk about in a little bit. It wouldn't be in the default one I wanted to be showing right now, but basically you just have default plugin without the word pure in it. and that's it. And that's like the simplest plugin. And that has two effects. One, it breaks safe Haskell, which I mentioned earlier. It's something that I like to use. And but if you just use default plugin, it breaks safe Haskell, and it also causes your module to recompile any module that uses the plugin is now recompiled on every build. It doesn't reuse the previous build. It's always going to recompile, which is a little annoying. So the next step up from that is what I call the null plugin, which just the only thing it does is set the value of plugin recompile to be a pure plugin, so that it doesn't force it to recompile. But the plugin does nothing else, right? It's just the minimum thing you can do. It doesn't affect your code at all. It doesn't add anything to any passes or to any phases. Like it doesn't add anything to the core phase or your type checker or anything like that. And so those are like the most basic things. And then, so even in even those examples, which you can't see right now, there is some tooling I've written to help with some of the pain points of plugins. That it is used in this. Oh, actually, it's not used on this branch maybe, but so basically, plugins. One of the pain points is that they're very fragile. They're in the GHC package, as you can see in the package import here on line 34. And the GHC package is not like a real version. Like the versioning of the GHC package doesn't follow like Semver or PVP in the Haskell world, but which is a semantic versioning. Because it's basically just exposing the internals of that version of the GHC compiler. So the versions of the GHC library are one-to-one mapping to the compiler, right? So if you're on GHC 9.14, you have GHC library version 9.14. And so any basically internal changes to GHC will have publicly visible changes to the GHC library. So even though as they version GHC, they're like, oh, these are non-breaking changes or whatever. We're just like, maybe optimizing some stuff or changing some things internally, but that can really break the GHC library. And so that can be really painful then if you're like writing plugins and you're like, if you're trying to write plugins for other people to use, especially if you're running it for your own application, you'd be like, well, this is the compiler we support, this is the GHC version we support. But if you're trying to publish a plugin, you want to support more versions of GHC, but again, it's very fragile. So I've put together this package called GHC plugin utils, which is not a great name. I would love a better one. It does a few things. Actually, if we go back to that again, we can scroll down. That's what this little help from my friend section is about. So this GHC plugin utils does a few different things, and some of it does better than others, as far as like how much has been implemented thus far. But it does compatibility across GHC versions. Normally, if you are trying to get a plugin to like work across GHC versions, you have a lot of CPP, a lot of like min version GHC, blah blah blah, and it has all the different they're going to have different like constructors and stuff in places. Functions take different sets of arguments, things have different structures. So this has a plugins module that handles all that internally, so that it can export a consistent plugin interface across many versions. I currently am only building it from GHC 9.6 up, but I think it might still work all the way back to GHC 7.10. Not that anybody's using that, but that's what it originally supported back to, and I think it might still support that far back. But anyway, I tried to paper over all those differences that the GHC maintainers don't really worry about when they're upgrading, when they're making changes to GHC itself, so that it makes it easier to work across different versions. It helps with some things like so we saw in the no recursion plugin that there are like options you can pass with that F plugin opt. In fact, if we go back to the code again, swap back one more time here, you can see right here on line 40, there's an ops structure that says like, oh, here's 4 different options I take. And then below that, there's like the default values for those options. And so just like opt parse applicative does for normal, you're writing a program yourself and it handles your command line options for you. GHC plugin utils has similar stuff for processing your F plugin options, so that you don't have to like redo all that code of parsing those things and like whatever. And it's like op parse applicative light, sort of very light, but I mean, but it does help with handling those options for you. And then okay, you can go back to the talk now. And the other thing along with that, along with the option handling, is a similar thing for source annotations, where yeah, it just has some helpers for like accumulating and managing your source annotations a bit, and it can associate them with options, so you can have kind of corresponding, oh, you can write the option this way or create the annotation this way, and by the time you see it, it's been unified into like one thing, so you're not caring about whether it's annotations or options that the information is coming from. And if you scroll down here, this next part is aspirational. This is sort of there's a library that I've talked about before, I think, called optenv-conf, which does like it's like op parse applicative plus handles environment variables plus reads configuration files for you and allows you to have this like consistent way of defining things regardless of whether they show up in config files or environment variables or what. And I kind of want to do the same thing, taking those like plugin option and source annotation bits and extending opt-env-conf, so you can also then use environment variables, access environment variables, and use config files for your plugins. So you can define, like I mean, whatever other stuff, but have, again, a consistent way that you as a plugin author can just say like, oh, I have this and it's available as, this environment variable, that and that and that. And then you just get that ops structure back that has, like parsed it all and decided like what the right set of things is. Again, like op parse applicative or this opt-env-conf, it just kind of does all that stuff for you. So as a plugin author, you don't have to be thinking about all that stuff, which is annoying. And also, if you're doing it yourself, you're probably doing it consistently with other plugins out there, and it's just kind of hard to what syntax that everybody choose for how to define plugins or how to define options and stuff like that. So, so to make that, you can scroll down a bit, bit more. Let's see. Yeah. So this next thing is about like kind of how to, or like how like these multiple ways of writing the same thing would, like users write them different ways depending on certain aspects. Like for example, as I mentioned, the annotation breaks safe Haskell. So some people would want to like write the options GHC version to keep safe Haskell working, and others would like to annotate specific functions that they allow recursion or not or whatever. And so you can have that mapping between the two. The next feature of the library of the GHC plugin utils is like this recompilation inference. So given like your definitions of your options and some other stuff about your some other like things you can do, it will determine exactly when the plugin needs to be recompiled. So it will calculate that. It'll give you a fingerprint function basically that will tell you like whether or not changes have been made since last compilation that require recompilation to happen or not. So that avoids some things. Like I call out here, like there's one provided by the plugin library or the plugin module, which is called flag recompile, which will recompile if your flags change, like if the options you pass to the plugin change, except that flag recompile sorts the options first. So if there was any significance in the order in which options were provided to you, like when you provide warning flags on a command line, if you like pass them in different orders, you'll get different results out, like whether you've silenced one after you've enabled W all and then silenced the specific one. If you put those in the opposite order and enable W all afterward, it's not going to catch that silencing. And so you can definitely have that kind of order dependency of your options, and the control that is provided to you by GHC, the GHC library, you lose like that aspect of it, for example. And so anyway, this tries to do a better job of determining when you actually need to recompile stuff. Because I don't know about you, but I find when things recompile and they don't need to, it like triggers a cascading thing of more recompilation and just like gets in the way of a lot of stuff and slows things down, and it's always something I'm trying to fix. Another thing in the GHC plugin utils is data passing. So there's no there's no mechanism, like I mentioned, that there's, you can do stuff at the source level, you can do stuff, you can just change compile or yeah, the command line flags that are like effectively given to the compiler. You can just like say, hey, I actually want this one to act like it's turned on. And then you have core and stuff like that. But when you make changes at any level, they're not visible. Like you don't, there's nothing that says that you've made those changes, or if you collected data at one level, like with the explicit for all, you might have, collected some information, and then maybe you want to take advantage of that information at a later pass. There's no mechanism for passing data through, but all of these passes, or at least most of the, I think all of them, are a wrapper of some type over IO at some level. And so there's some tooling using IO refs to allow you to, capture data at one phase and then access that data at a later phase when you're doing something else. So again, that's captured in the library. And dynamic loading, which is a really fun thing that was hard to figure out the first time around, and is actually just a pretty wonky thing. Or, I mean, it's Haskell, we have a lot of types. And so dynamic loading is like, you're basically pulling in code externally and like being like, hey, I think this has this type, and maybe it should compile and whatever. So the complicated plugin I've written, the categorifier one, and as I mentioned, it compiles on the C, but it gives you a lot of flexibility in like how you compile things on the C. There are times when if you use certain third-party libraries that you might need to manually, or you might benefit by adding certain manual definitions about like how certain functions in that library should be converted. And when we're doing the C conversion and stuff. And various things like that. But there's a lot of things where basically we want the user of the plugin to pass an option to the plugin that says like, hey, here's a term I wrote in some other dependency, right, that I want you to use to give you like the list of other things that need special handling or things like that. And it's not like regular user Haskell code, so you can't just like define a type class and then like have people write instances of that type class or whatever and do like stuff like that. Like for extensibility, you're basically passing in a string naming, some identifier, and saying like, hey, find this identifier in this module, and then, try to like load it and use it in here. So anyway, it's a complicated thing that can be really useful in plugins to be able to load code from the user and do stuff like that with that in your plugin. But it's not very easy to do. And so this is another thing that this package does. It just kind of encapsulates the complexity of dynamic loading stuff, and ties in with the option parsing stuff. So it's like knows it's parsing an identifier that should be handled certain ways and stuff like that. And so yeah, so that's another thing that this GHC plugin utils library does. I was hoping that it would be published before I gave this talk, but it is not. I mean, definitely not all of the stuff I mentioned there before, like the opt-in conf stuff is not there, and some other things are only partially done. But all the pieces that I have extracted out of categorifier for the dynamic loading and stuff like that, and from no recursion and all the option handling stuff, like that should be published soon. Although I wouldn't mind a better name before it gets published. So if someone has a better name than GHC plugin utils, that'd be great. But using that library, I think the main thing you would notice right off the bat is just not having to do a lot of deep preprocessor and conditional compilation stuff. Even importing, even just the plugin module itself has changed names and like where things are defined in there. So just your imports of like plugins in the first place, like would be conditionalized otherwise. Oh, and in the safe Haskell vein, a lot of the plugin modules, or plugin related modules, are not safe directly. So the GHC plugin utils library does a lot of wrapping to make those things safe so that you can use it in safe modules. Which granted it is like, yeah, it's not, I wouldn't say it's perfect, but it's like once you have unsafe code, you can claim it's safe, but there's always some chance that something's going on in there that you're not taking account for or whatever. But it tries its best to kind of capture that stuff and isolate it. But yeah, I think it's a useful library to use if you are writing GHC plugins, and again, should be available soon. And I think this last point that's in this part of the talk, I've kind of already gone over a bit, which is the different representations, like different ones. Like we looked at core, but the different phases had different representations, and so you kind of have to like poke through each one. I feel like they're not very well documented. They often will like have a comment that shows an example of the syntax that results in that, that particular construct. Um, but those aren't always obvious. In some cases, they don't exist, um, and things like that. And there's not a lot of description about like, when exactly certain substructures are used or whatever. Um, but um, but yeah, I mean, it doesn't take too much to figure those things out. And once you do it too, you have like a much better understanding of just how GHC goes about doing things, which is, I think, really helpful. Um, and yeah, and with the library, I think it becomes pretty easy. It tries to cover over all the kind of complexities I've run into in different plugins and stuff like that. Unfortunately, again, I don't really have the simple cases that I had been building up with the default to null to like a simple use um, um, of the plugin library and stuff like that, the plugin utils. But um, but the idea the idea that I'm hand waving at here is that really it's not that much to especially with GHC plugin utils, to get something small working. You can incrementally start like adding to it. You can just kind of play with things pretty easily. And again, there's some tooling to help with that, but yeah, it's not like you're making deep changes to the compiler. You kind of poke around at these different representations and make some very useful. I've definitely found a lot of use out of it. Um, Changes to make GHC do what you want it to do. And yeah, like for just to come back to no recursion here for a minute. I mean, I the reason it's called no recursion is I think I mentioned this early on is that it's kind of like a pun on the language extensions. You might have like no implicit prelude, right? By default, implicit prelude is on, but no implicit prelude will disable it. Or you can tack no onto the front of various language extensions to disable them for a certain module. But the process of like implementing and doing a RFC and stuff for making changes to GHC itself, for getting a new extension in and everything like that, um, can be a lot. Like there's definitely a lot of overhead to it. There's a lot more stuff you have to be careful of if you're changing GHC itself, and you have to like work through a lot more stuff. And that's what I was thinking. I was like, oh, I really like to get this done. I want to do this at some point. I want to do this at some point. And at some point, it clicked in my head that like, oh wait, I don't actually need to modify GHC. I can just pretend, like I can just make this plugin pretend it's like a language extension, basically, and do the thing I want outside of GHC and not have to be involved or in that process. And maybe at some point it does move to that level, but at least with this, it's like um, the first version of no recursion I wrote in a couple hours, um, and uh, and it worked, and I could just use it on projects, see how it was affecting them and everything like that. And I could just plug it into existing GHCs. I didn't need to like do any kind of rebuilding of GHC or like other stuff like that. So it was like there's like you can now experiment and you can do all the stuff with it. And maybe there's some of those edge cases that I mentioned that I won't be able to like swing with the plugin somehow. I'm not sure. Um, or some other reason to make it like more properly a part of the compiler. At which point, like it would be worth taking that step. And at that point, it'd be like, hey, this exists. You can try it out. Like these people are using it for these things or whatever. And so you have like a much better case at that point too. So again, this is just kind of like a later way of making changes to GHC without having to kind of commit to that process or anything. Um, and yeah, that's a lot of stuff and more hand waving than I was hoping over code, um, but yeah, you should try writing some plugins. If you do, I'm happy to talk you through things or like add things to my utils library that could be helpful.
Do you have
Yeah.
access to comments? Code
To what?
comments? Do you have access to code comments
Oh, to
in the
comments.
plugin?
Oh, I don't know if you do or not. I mean, if it would be in one of the early stages, obviously, if it were, but like you mean like I mean like Haddock. Well, I don't think you ever have access to code comments, like straight up comments. You might have access to Haddock. Um, I'm not certain.
Okay.
But yeah, actually, I'm really not certain now. Yeah, that is something that I've been curious about though, but I haven't actually ever looked into. Is there something specific you want to do?
No, just kind of pretty powerful if you can sort of impact how the compiler works in the
Yeah, I
comment,
mean,
right?
yeah, it would be nice if there were comments there. I mean, I know I've been frustrated. I haven't looked at this with GHC, but with like other compilers, other languages that like, they always discard comments like
So,
so quickly.
no,
Um,
I haven't looked into liquid Haskell for years. But where do you put annotations for liquid Haskell? Do you guys know? Remember?
yeah, it's something else I haven't looked at in
You
literally
put
years as
you
well.
put it in the comments? Where do you
Uh,
get the
Hold
annotations
on.
from?
I think it is in comments. Yeah, let's hold on.
So
I'm
how
just
do
loading
they
up the
get it,
docs right
right?
now.
It's like this sort of curiosity.
Oh,
Why is it like
no. Okay. So, oh yeah. Okay. So I think you do have access to comments at a certain level because I think Liquid Haskell actually does um like a syntax plugin. So it defines new syntax. Um, or is it just a comment? Let's see. I don't know if this is actually new syntax.
I'd
I have
have
to look
to
at the
check
source,
it.
but
Yeah.
Um, but it uses a syntax like the language extension syntax, except that or the pragma syntax, except that it uses an at sign instead of a pound sign. Um, and so I don't know if that gets parsed as a comment first and then is like specially handled after the fact, or if that's actually distinct syntax from a comment. But it would be nice to access comments anyway. Um, yeah, especially like if you're doing something that like like rewrites code and stuff like that, you want to be able to like hold on to those um, and spit them out in like, the most correct place in the new code or whatever.
Yeah, also
Um,
like you have this what I'm using a lot, this execution building, right? You have the you have in the command you can put the you can put a piece of code which gets evaluated. Then it gets evaluated by what's the name of the plugin?
oh, the doc test,
Doc
that one,
test. Yeah,
or
yeah,
but
exactly, right?
but so
So
doc test doesn't work as a plugin, right?
doc test
It's
is
like,
not a plugin, right? It's more
yeah, yeah,
small, but more on there are two different versions of it actually.
yeah.
But yeah, but stuff like this, messing with stuff you put in the comments in interesting ways would be sort of seems like
Yeah, I mean, I feel like there must be a place early enough. One of the hooks must be early enough that you can actually access comments. But yeah, I haven't actually tried in GHC. But yeah, like I said, like in other languages, tried to do stuff and been like, oh, it's already thrown away all this like information that I want to hold on to. And yeah, but those don't have, like those have been cases where they don't have real plugins, say like, so, I am just kind of hacking things in the comments and then hacking on the compiler to like, do stuff or whatever. Um, yeah, I would like to find that out for GHC. I don't know.
yeah.
But
So
yeah, I think that's it. I mean,
liquid Haskell doesn't use storage. They
sorry, it doesn't use comments, you said?
does not no. They
Yeah,
use
okay.
the dash at
Yeah,
dash um, so
yeah.
oh,
Um,
yeah.
but yeah,
So
so for not being able to actually share most of the stuff I wanted to share, I think this went all right.
no,
But
my other question. So
yeah,
the whole thing started with the recursion, right? No
yeah.
recursion, which is great thing, obviously. Um, but the question kind of comes to mind: when does recursion is when recursion is good, right? When given other choices, you still want to do explicit recursion.
Yeah, I mean, I don't know. It's
And
a good question. I
I
definitely am
was
still
yeah.
struggling to manage to get rid of it as much as I would like to. Like
So
I feel like that's like we're not at a point where I
one
even,
of my
yeah.
answers to this
What's that?
is my answer one of the answers one of the
Okay, yeah.
I want to answer it in one way, right? It's not maybe not the best answer or not the only answer, but one reason I like to see recursion is because it allows me to do equational reasoning sometimes. You can't do equational reasoning with a fold. You're working on a list and you want to prove certain properties by writing a bunch of equations. If you use pattern matching and do recursive call, you can do equational reasoning with simple induction.
Yeah, right.
You can't do it with fold. You can't do it with recursion schemes. You can't do it with other means because the equation you don't have equation.
I don't know. I feel like you. Oh, I see. I guess I see what you're saying. Yeah.
Yeah, for example, you want to say you wrote a list reverse in some way. You want to prove that the length has not changed. Now, if it's recursive, it's trivial because it's a bunch of equations.
Yeah.
And you apply length on both sides, it will be the same. Or if you do something like a list append, right? Two lists append to each other. You want to verify the length of the first and the second. Adding the length of the first and second gives you the result. Again,
Yeah. So
trivial equational reasoning.
I feel like you get that with, I mean, at least the way that I think about recursion schemes often is that the recursive term, like the part that represents the recursive term, is like that is the result of having applied those rules recursively, right? So like you still have like a step for the, for the zero case and the n+1 case, basically. But instead of like making an explicit recursive call saying like, and now I'm going to like refer to the same thing again, you have this assumption that like this value here is the result of having made that recursive call already, and I only need to prove this one step. So it is like so I feel like it has that one-to-one mapping to the direct recursion, or can at least.
Mm.
Um, but yeah, I think
Yeah, no, no,
yeah,
I'm
one of
not
the things
sure I
that
understand, but yeah, let me
yeah,
follow
that's
you.
like another talk. We can sit down and,
Yeah, yeah,
go through
yeah,
we
yeah.
can sit down and go through like various recursion scheme stuff. But yeah, I mean, I'm curious because I would like to show you what I think about that, and see where you think that does or doesn't line up with what you're yeah, with your equational reasoning there.
I guess on my end, I probably need to give you a better example. I'll try to
Yeah.
put it in
Um,
the matrix. Where
but
good
yeah,
example where equational reasoning will be kind of nice when you do explicit recursion.
yeah,
Just kind of on the face value, it is nicer because your definition when you pattern match and use recursion is basically a bunch of equations,
yeah, for sure.
right? So it's laid out as a bunch of equations, and now you have equations to work with, and you can do inductive reasoning.
Yeah.
Yeah.
Yeah, I was thinking about oh, what was it? Oh yeah, just so with this no recursion thing, one of the things I try to do is with that plugin in particular is replace definitions with either non-recursive ones, yeah, generally. And one of the things that's frustrating with a lot of the base library, at least, and I mean all of Haskell really, is because since everything is there's list is so fundamental, and everything is that since list is lazy, so many of the types are just um, like I just can't, it's like impossible to define a total version. So like this s concat is like one example. Like it comes up as like, oh, it's a recursive definition, and like s concat takes like a list of of semi-group values and puts them all together, um, but the problem is that that list might be infinite. So like your fold is potentially non-terminating, and there's no way to like I can define alternatives to esconcat that instead of taking a list, take a strict list, right? So it has to be finite, and then can define that using recursion schemes or whatever. But there's no way for me to define an esconcat that is total because it's always possible for that input list to be non-terminating. And then so anyway, I hate cases like that where it's like, all I can really do in this case is ignore the fact that there's recursion, because even if I wrote a non-recursive definition, at some point I am, you know, Well, I don't. Yeah, I mean, it would be recursive at some level, I think, because I don't think there's any way for me to rate that without at some point just getting down to Haskell's built-in recursion to execute that. I mean, I can kind of push it down a bunch of layers and like eventually use like an unsafe kata or something like that that actually does use recursion under the hood, but it doesn't buy you anything in the end because you're still stuck with that. So yeah,
So,
anyway.
so I think so. Um, there's this term. What term I'm looking for? There's this. So, um, uh, you kind of have this weak termination aspect where you're dealing with infinite stuff. It's okay as long as you keep
Right. Yeah.
keep
Yeah.
producing stuff, right? Well,
Right.
with the infinite list, it should be okay as long as you keep progressing,
Right. And
right?
that's the problem with like a definition like Eskin cat is there's no, you're not exposing anything that allows progression, right? You're only exposing a
Yeah,
final completely folded term. So there's no like
right. So
you can't like
yeah,
expose something incremental that you can then choose to apply as many times as you want or whatever, and get that kind of co-recursive aspect out of it.
mhm,
Because you've given a potentially infinite thing, and the result is a very finite thing. You're just
yeah,
forced to do that impossible step basically. And the same thing happens in like other type classes like is list, just converting to and from lists. It's easy to convert um, like co-recursive things are fine. You can convert it back and forth. But if you have a strict list, you can really only convert it to a list in a total fashion. But you can't go from a potentially infinite list and get a strict list out of it, right? So you can't really
mhm,
implement is list in a total way, at least for strict lists and things. But anyway, yeah, there's a lot of things just in trying to eliminate recursion where you just kind of like eventually run up against base or whatever. And it's like, well, do I replace base or do I just like satisfy myself with like ignoring a few of these problematic cases or whatever. So far, I've been doing the latter, but I am always tempted to like rewrite base in a more total way and and see what I can do there. But that's quite an undertaking. Maybe just prelude to start. Everybody likes to write a new prelude, so. But yeah, all right. Well, I think we can. I don't know. You have any more questions, Nick or Robert? Anything else?
stop sharing, and maybe I'm still recording.
I'm good.
Well,
Yeah.
Thanks, Greg.
yeah. Thanks.